I'm Thomas Edwards. I'm a Senior Manager Solution Architect at Amazon Web Services. I run Direct Consumer and Broadcast Specialist Solutions Architects in the Americas. And we're going to talk quickly about the situation for software media exchange, which has been discussed a little bit earlier. A little bit about the EBU Dynamic Media Facility. A quick introduction to Libfabric, which will be a quick introduction because you could probably talk for hours about the details of Libfabric. I'm going to talk a little bit about the AWS EFA Libfabric provider. We'll talk about the potential for a media exchange SDK and then some questions. So what is really the requirements for live production media exchange? You've heard some from some of the users. I want to try to give my viewpoint on this. I think the king is reliability and quality, no loss, right? You pay a lot of money for the material that you're recording, and you want to make sure it's 100% there and getting to the end users. So, we do have some packet loss in the cloud, right? It's very rare, but it happens sometimes. In any internet transmission, you're also going to have loss, and that's why we have things like SRT and RIST or SMPTE 2022-7 dual paths for seamless failover. You need low latency. Now, exactly how low depends on exactly what you're producing, but the lower seems to be the better. And we'd like to have efficient transport. Instead of using a whole bunch of cores for the transport, maybe we're just going to use like one core for the transport. The more efficient, it means the more affordable it will be for users. So why are we here? Didn't we get 2110 working? Didn't we spend a lot of time on that? Over the many years of networking has gotten faster and faster and faster. And when we were first talking about SMPTE 2110, it was in the world of where you had 100 gigabit Ethernet. And boy, that seemed really fast, right? You could easily put 50 HD channels onto your 100 gig Ethernet. Have a whole switch of 64 ports of that. Holy cow, that's bigger than any router that's ever been built. And then came 400 gigabit Ethernet. And nowadays, if you go on YouTube, you can watch somebody unboxing and doing an 800 gigabit Ethernet switch review. Okay? So the bandwidth is there. We've got tons of bandwidth. But what's the problem? Why isn't 2110 in the cloud and everywhere right now? So our big problem is that the single thread performance of our cores just stopped getting bigger. The number of transistors has been going up following Moore's law, the number of transistors on an entire chip. So that's working out really well. But the single thread performance of a core, it was getting faster and faster. And once it got to a couple of gigahertz, it just flatlined. And that's what our challenge is. Our challenge is with things like 2110 is that pure software packet pacing accuracy has significant limits due to the limits of the core frequency. So yes, we can throw a lot of data out there, but our accuracy to be able to tell exactly when to send it out there is limited. So this implies we may want to concentrate for our software media exchange at moving frames within a frame time rather than moving subframes within a subframe time. Now, obviously, this influences the way that we're going to be processing this media. It means we have buffers. We may want to move to asynchronous models. But, instead of going line, 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 we might want to do frame, frame, frame. As long as we're getting a frame out within a frame time, we're delivering the media as we need to in order to process it. So, we have plenty of bandwidth. We can give you an Amazon P5 instance that has 3.2 terabits per second of networking on it. Plenty of bandwidth out there. And we can give you timing within millisecond accuracy. We're working on microsecond accuracy. It's delivered in some parts of the AWS EC2 world, but all AWS EC2 instances can definitely give you millisecond accuracy to UTC through our Amazon Time Sync service. So we've mentioned briefly the EBU dynamic media facility. I won't go into too much detail, except, the concept here is to be interoperable, platform and hardware agnostic to use the software media functions. I think that's the key that we need to keep in mind. As we take a look at the dynamic media framework reference architecture the EBU's put out, they're talking about, compute network and storage with clusters of compute nodes, containers running on those compute nodes, then some sort of high performance asynchronous media exchange, likely including uncompressed media, because uncompressed is the best. No one can argue about the compression artifacts in uncompressed media. Functionality on media through media functions, and at the highest level, users carrying out that functionality. So this is a great stack model. I'm super excited about this. So what I'm here to talk to you today about is that bit right there, the media exchange. So in the dynamic media framework, media exchange reference architecture, they talk about the video payloads. I think we mentioned again, why did we do P groups? P groups was a very easy way to map what we were doing in SDI to what we were doing in 2110. And it was bandwidth efficient and it made lots of sense. But the truth is, this isn't going to be an SDI replacement, right? This is going to be something completely novel where we can really go back into the software and we can do what we need to do to make software work, not just to make an SDI to 2110 converter or a 2110 to SDI converter. So their suggestion is to go with 16-bit planar YUV and specifically not to do 2110 P groups so we don't have to pack and unpack to align 10-bit data with 8-bit bytes. I think it makes some sense. We have to have a lot of discussion about this, though. And in their roadmap, in their dynamic media facility reference architecture, they talk about their minimal viable product, their phase 2, and their stretch goals. For media exchange, they talk about using shared memory for video audio data payloads, and maybe in phase 2, using shared access via RDMA over converged Ethernet, or some people say ROCE. And if we look at what they're trying to do in the minimal viable product, they were talking about a frame of video, and then maybe in phase 2, move to subframes. So I think this is a good place to start. There's nothing wrong with shared memory. The problem is you're going to run out of it because virtual instances are only so large, right? At some point, you're going to need to go over the network to another physical host. So the high performance computing world has been dealing with this for a long time, and they have a lot of compute nodes out there, right? They don't all fit onto a single physical host. They have to have multiple hosts connected by high efficiency networking. Now they came up with all kinds of great networking technologies. For them, Ethernet was too slow, so they came up with InfiniBand. And in 2000, the InfiniBand Trade Association created their verbs specification. So a verb is kind of exactly what it sounds like. It's what you do on an InfiniBand network. For instance, you send a message or you receive a message, and then there's some control functionality as well. They realized there needed to be a software implementation of this. So in 2004, verbs was implemented by the Open Fabrics Enterprise Distribution from the newly formed Open Fabrics Alliance. So that later evolved to cover iWarp, which is RDMA, and that's again remote direct memory access. It's a way that data can flow from the network interface card directly to memory without bothering the CPU. So iWarp is RDMA over TCP, and then there also is RDMA over converged Ethernet or ROCE. So in 2013, the OFA started the Open Fabrics Interface Working Group. And their goal is to try to find an API that was really independent of the network technology. Because by now there had been, there's InfiniBand, there's Ethernet, and there are like a handful of other high performance computing networking technologies. So they wanted to abstract that API to really concentrate on the application requirements. And they spent months collecting these requirements. And then in 2014, the result was the Open Fabrics Interfaces, or OFI. And OFI was implemented by Libfabric, which is open source on GitHub. So Libfabric has some key points to it. It's message passing. You send and receive a message, a block of bytes. It's not a byte stream like TCP. They try to go for zero copy, meaning memory-to-memory transfers without buffering or copying unnecessarily. They try to use RMA, remote memory access, again, those NICs, which are reading directly from or writing directly to memory without bugging the CPU. A key element of this is memory registration. As you know, in the world of virtual memory, which is in the physical memory, gets paged in and paged out of the physical memory. So if the network interface card is trying to write directly to memory, but that memory page was paged out, that's a problem, because then you're going to have a page fault and the CPU bring the memory back into the virtual memory back into the physical memory. So what you do is you register that memory in physical memory, so it's stuck there and it's not going to page out or become remapped. Kernel bypass, so it's direct user level access to the hardware without doing a whole bunch of complex OS calls during the data transfer. There's lots of wonderful things that for instance, the Linux TCP stack does for us. But when you want to move data really, really fast, you don't want that extra help of sockets and the TCP stack and all those things. You just want to push that data out to the network or suck it right back in directly from user space. Asynchronous operations. So this says send the data and then come right back. And you can keep doing computations while it's sending the data, or same thing for receiving the data, or doing multiple simultaneous transfers. And the last is what I think is the most powerful element of Libfabric, and that's providers. So the core Libfabric is definitely a set of APIs, but they are truly implemented by the provider for the particular fabric that you're running on. So if you look at the stack at the top, you've got your high performance computing applications, whether you're measuring the airflow over an F1 car, or whether you're doing hydrodynamics of a boat or what have you. Then comes the middleware. This includes things like the message passing interface, or MPI, or the NVIDIA collective communication library if you're doing artificial intelligence with GPUs. Then comes Libfabric. And between Libfabric and the network interface card, you've got providers. This is a provider for one fabric, provider for a second fabric, provider for a third fabric. Depends which fabric that network interface card is going to be on. So today you've got the verbs provider for Libfabric. So this is going to cover your Roki, your InfiniBand, and your iWarp. You've got SHM, which is shared memory, and we were mentioning shared memory earlier. There's a shared memory provider in Libfabric, and it can even use a Linux cross memory attached so that one process has access to the address space of another process. There's EFA, the AWS Elastic Fabric Adapter. Sockets, this is mainly for testing because it's not super highly performant, but it does work. In fact, you can even do this on your laptop. You can use Libfabric with sockets provider if you're running, say, like a MacBook or a Linux on your Windows system. And then there are the other high-performance computing fabrics, Cray generic networking interface, performance-scaled messaging for Omnipath, user space NIC capabilities of Cisco UCS, and IBM Blue Gene Q, in case you have one of these in your backyard. I want to talk a bit about the Amazon Elastic Fabric Adapter because I get some questions about this. They're like, hey, why aren't you just using Roki in AWS? So this was designed for the needs of our high performance computing and machine learning customers. AWS specifically chose not to use RDMA over converged Ethernet because it requires priority flow control, or PFC, and this was felt not to be really feasible on large-scale networks because of head-of-line blocking, congestion spreading, and deadlock problems. And they felt that even our Roki would still suffer from potential ECMP collisions inside a large network. So they said, let's just make something that works on a huge network like AWS. So that's why they went with this scalable, reliable datagram protocol. And also they decided to allow out-of-order delivery to avoid the tail latency problems and head-of-line blocking. And that means the higher order layers have to deal with that ordering, but the lower layers don't have to worry about it. And it uses the Libfabric interface. So it's halfway there. It does OS bypassing networking with direct memory access. So quick reminder, I know some of you know about this, but the scalable reliable datagram protocol takes a flow and sprays it, which is the term of art apparently, sprays it across 32 different paths. And each path has different encapsulating headers, which gives each of these sprays a different ECMP hash and thus a different path through the network. It avoids overloaded or failed paths by measuring the round trip time on each of those paths. And if you see congestion or you see an outage, you can just rebalance the traffic off of the failed path onto the better paths. So this is the Libfabric object model. The fabric is the hardware and software resources of a single network. That's really the network technology that you're running on. A domain is a logical connection to that fabric, so that could be a virtual network interface card. It has passive endpoints, and these are used to listen for connection requests if you're doing connected transport over Libfabric. I think for what we want to do, we probably want to use unconnected, so we'll probably not have to worry about that. I'll probably use datagrams as messages. Active endpoints are the portal for data communication, and you can think of active endpoints kind of like a socket in TCP/IP. And because of that asynchronous model, there are queues. So there are event queues, which report completions of asynchronous control events. And there are completion queues, or CQ. Those report the completions of data transfers, either reads or writes. If the completion queue is taking too much time for you, you can use a completion counter, which is a lightweight alternative to the completion queue. There's an address vector, which maps high-level addresses, such as IP addresses, into fabric-specific addresses. So even if you're running on a fabric that has no concept of IP or Ethernet MAC address, if it's something crazy, the address vector can perform that mapping. And then there's the memory regions. So this is when we're registering memory so that it's not going to get paged out of physical memory. So just for fun, again, I'm not a developer, so I just took the FI ping pong, I think it stands for Fabric Interface ping pong test, and this comes with the Libfabric library if you download it and install it, to see what happens going between two EC2 instances on AWS. So FI ping pong just uses a single vCPU. Was sending reliable datagram messages, RDM. Again, we implement that using the scalable reliable datagram protocol. If you're doing this on your home computer, it might use some other mechanism. Sending a message size of a 1080p 60 422 10-bit uncompressed frame. And I found we could easily do with a single vCPU well over, well, I would say well over, but over 10 gigabits per second over 18 hours. So it's like about 2.5 the real time of 1080p 60. If someone actually who was a developer and went in and did this in a more optimized fashion, could probably even get better functionality. If you need more than 10 gigabits per second, you can use another vCPU. So this is a concept for a potential media exchange SDK. I think this is some of what Felix was talking about. It's nice to have an open source SDK. It makes great sense for software. We've seen great success with the NDI SDK, which is not open source, but because it's an SDK, you download it, you run it, it works. Someone else downloads it, you have a very good opportunity for interoperability, probably more than a standard or specification. But I will say by being open source, it means that you have the ability to have much more observability into what's going on within the SDK. We like to have a target set of tested Libfabric providers. So I mentioned, I don't know if we're going to test on IBM Blue Gene, but let's at least test with like the shared memory provider, the verbs provider for InfiniBand. By the way, there's another cloud that has InfiniBand instances. I don't know how they do it, but they do. Or RDMA over converged Ethernet at home. And also the AWS EFA provider. We'd like to test on that as well. I will say the AWS already has a high efficiency uncompressed media transport called AWS CDI, which runs really well on AWS. To date, nobody's been able to port it elsewhere. It also lacks a couple of bits of functionality, which I'll address in a second. I think we probably are going to use a reliable datagram endpoint type that happens to be common to all of these providers, and I think it makes a lot of sense. I don't think we need connections. I would recommend that we implement the VSF GCCG API, maybe not P groups, but otherwise, in order to have the timestamps and other metadata and the media functionality timing that we need. Now, what I will say AWS CDI lacks is registration, discovery, and connection management. But fortunately, AMWA NMOS has got that. It's there and it's ready to go. So we should plug into that. You transport uncompressed media. And we might want to have some compressed media. We might want to have JPEG XS, or we could even have high throughput JPEG 2000. If you're going to send a whole frame, high throughput JPEG 2000 across the whole frame may actually be a more efficient compression than JPEG XS, which is subframe, plus there is no royalties to high throughput JPEG 2000. Sorry, Ben. Now we just need to write the SDK. How hard? How hard can it be? It's just software. What'd you say?
How hard was it?
How hard was it? No. That's all I've got. Thank you so much.